Hi, my name's Scott Shadley. I'm the VP of Marketing with NGD Systems. You may ask yourself, what am I doing standing on the bridge of the USS Discovery? Well, I think about the fact that the future is now, and that these cool technologies that were introduced in television programs like Star Trek and other futuristic activities are really not so far off from where we are today. So I want to spend some time today talking to you about a term, computational storage. Now, I titled it Computational Storage at the Edge and Beyond because this solution and these products and technologies have the capability of supporting architectures in many different landscapes, many different footprints, and of course, scalable across all of them. So I wanted to spend some time with you today. And I know it's a virtual event, so I was trying to have a little bit of fun, make sure that you're engaged and entertained. We're going to spend about 45 minutes here together. It's going to be me, a few of my friends talking, especially my end customers. And we're going to walk through for you a little bit more about what's going on in this architectural space. So, a lot of people ask, what is it that we need this technology for? And of course, it's always a question that we want to answer for our folks and for everybody in the marketplace today. So, we have this thing called von Neumann compute, memory, storage, three unique elements. And they've been that way since the 60s when this architecture came out. That's exactly the same time the first Star Trek series was released, just in case you're curious. Back then, they were using nice little plastic cards to represent data storage on devices and the fact that they are the equivalent of a USB stick for today. So, again, technology is all relative. Star Trek's a great tool, and it's a fun way to start these conversations. Now, when I look at it, you can think about the fact that we have one, maybe two CPUs, a whole bunch of cores, a lot of memory, and then a ton of storage in these boxes. We came up with this idea about composing these architectures. Great. New technologies, new efforts, we can do things like that as well. But we still run into the problem of space, really starting to run into problems with power. We're worried about the scale of these solutions. And of course, there's this concept of the bottleneck shuffle. If it's not in the storage, it's in the networking. If it's not in the networking, it's in the compute. If it's not in the compute, it's somewhere in the platform. So what we want to do is talk about an architecture that helps resolve these problems and makes your life as the IT administrator, IT developer, application execution writer, all of those situations better. Now, when we think of flash storage, everyone likes to think about the concept of NVMe. NVMe is great, but it's just like we see in any modern infrastructure today from a roadway perspective. You add more lanes, you add up the speed limit, you still clog the byways and the sideways and the other ways. So we need a way to help relieve some of this stress. We're generating 175 zettabytes of data by 2025. And I guarantee it's going to be more than that, especially now that we're stuck in this COVID stay at home, everything streaming virtual environment. This would be a live presentation face-to-face if it weren't for this type of an environment. So you wouldn't have previously needed to store this as a recorded presentation. So storing data is easy. Working on data is becoming more challenging, and how we work on it, where we work on it is a much more involved aspect. GPUs, DPUs, they add value. They have their place. So does computational storage, and we're going to hopefully explain to you throughout this presentation as to why that is valuable and important to you. So what we've done with this concept of computational storage is we allow you to do distributed processing, allowing you to work on data where it is stored, getting faster results, saving power both on CPU and transit, and able to reduce the footprint because you don't have to have all of these different components in the same scale. And we'll walk through multiple examples of that as we get into the rest of the presentation. So we've built a server and a server. Our computational storage solution is one of many. As a member of the board of directors for SNIA and the co-leader of the computational storage technical working group, I get to see a lot of what's coming down the pipe. If you're not already a member, this is a quick plug. It's a great opportunity to get involved and be a part of what's going on in that space. But what we've done is we've added CPU resources into the storage device itself. You store massive amounts of data. You really don't want to move it. And that's what we're helping solve. So from a perspective of an architectural point of view, you think about it as past, present, and future. Again, I'm kind of going off this concept of sitting on the bridge of the USS Discovery, right? The old way works, the new way works. They're both here today, but the future is really going to be deploying things like computational storage and other architectures like that to help alleviate some of the problems that have existed in our storage infrastructure for many, many years. And so it's about the innovation of technology, not sticking with traditional technology. We're in a perfect world and environment to actually drive forward significant amounts of innovation, and we've got a lot of opportunity to see that happen with the concepts of computational storage solutions. So when I talk about that, I want to look at the different ways that we're deploying this product, right? So I can tell you all kinds of fun ways to use it. I need to know how you would like to use it, what you're trying to accomplish, and what your pain points are. This list of applications, workloads, tools, OSs, all of these features that you're seeing here on the screen, anywhere from a simple database to a search algorithm to big data, all involve customers and case studies that we've worked on with our customer base. We have always targeted multiple markets. We've said the edge is always going to be a perfect play, letting you know, folks, we won a contract to put SSDs with compute in space. That's getting to the edge. Autonomous anything. Autonomous cars are starting to generate massive amounts of data. They don't want to move it all. You can't move it all, especially if we go to a truly fully autonomous environment. We'll always continue to support the data centers and the CDNs and other large scale infrastructures. And then, of course, as we get into the concepts of IoT and other architectures around that type of space, the smart cities and automation come into play. So I've got a whole bunch of things on here. I would traditionally in the United States call this a NASCAR chart. It's a race car chart, all the logos that get stuck on the car. We're trying to highlight the value that we bring to the architectures. So now let's spend some time on the edge. So the edge is where the meat and potatoes are for this type of architecture. This is where we're going to see the significance of these technologies move forward. And a lot of this edge focus and a lot of these workloads, applications, and solutions are coming from our wonderful friends in the market in India. So the first one I want to highlight for you today is VMware. VMware is working with us for a special project. It's currently looking about 70% savings on the entire amount of rack space required and about 50% TCO. It's still a work in progress. This is something that's fairly new and innovative for us. We're trying to drive some new architectures and solutions here. And I'm actually going to take a few moments and let my good friend from VMware out of the office of the CTO spend some time explaining this to you. So I'm going to go ahead and switch over to a recorded video of him explaining this at VMworld 2020 so you can understand better from a customer point of view how we bring significant value to these particular products and solutions. So give me one moment and I will transfer over to that.
So we have a project that is in tandem with a partner, NGD Systems, and this is exploring a brand new technology called computational storage. This is one of our partner co-innovation projects that's in flight, and this is a really significant project because there's a movement toward bringing compute to storage. As the amount of data proliferates due to IoT and video use cases, particularly at the edge, there's a need to bring the compute closer to where the data is generated. And this is even true inside a host. Instead of moving all that data from storage through the main CPU and back, the new model that's emerging around dense data is computational storage, where you have a compute node that's directly on the storage device itself. So here we see an NVMe device that NGD Systems produces, and here in the middle of it, you see an ARM processor, an A534 core with 8 gigs of RAM, running its own instance of Debian Linux. That OS instance has direct access to all the storage on the device without needing to bring it through the PCI bus to your main CPU. And what we're doing with this project is we're actually testing it in tandem with our Greenplum parallel database structure. So we're running instances of Greenplum nodes on these ARM processors across a set of up to 15 devices. This allows us to run the Greenplum database with its integrated analytics directly on storage, completely freeing the host CPU to run the application and other functions. This is great at the edge where you have limited host CPU and you want to maximize that, and this offloads it to the storage device and allows you to get more parallel compute capacity. Rounding it out, we're exploring in this project the ability to use BitFusion to actually GPU enable these ARM processor-based instances. So BitFusion operates by sharing GPUs across the network. In this case, the network actually flows between a VM that runs on the host, the x86 host, and it actually creates a network connection across the PCI bus by encapsulating TCP over NVMe. And in that way, these Debian instances running on the NVMe storage devices become separate computers on the network, and they can actually talk to the Bitfusion server. So now you have a storage device that believes it has a GPU locally. And the Greenplum database can actually leverage that to do ML inference-based parallel queries running entirely on the storage fabric inside a host. So this is a really disruptive new approach for edge analytics. It increases data density, and it leverages core VMware technology such as Bitfusion and our pass-through technology as well.
So again, as you can see, compliments of Daniel and his team, we've got a lot of work that's been done on this particular architecture and project. There's a lot more coming from it, and of course, I'll provide some content and details of that. Here's an example of some of that content as it was presented within the full 1 hour presentation at VMworld 2020. So if you're really interested to know more, feel free to contact us, or we'll provide the link on our website in our resources section. So the next thing I want to talk to you about today is this concept of content traffic control. And the reason we talk about this at the edge is because as you and I are looking for our content and for our data, that data is going to be stored at a point that is not just in a data center. And so what we're talking about in this particular case is streaming content. The value we bring into this particular architecture is greater than 50% performance enhancement to this particular application within the overall infrastructure, and a 10% or greater overall system improvement. So you get your video shared to your local system 10% more effectively and 50% faster to route than it has historically looked at. So what we're seeing here on the top is the number of users being simulated by the environment, and this yellow line represents the latency that's generated to have that high level of user be told where to find content and how to deliver it. And as you can see, we're 50% more efficient using the computational storage drives. And as we add users, it's actually learning and actually able to drive a better distance between those two architectures over time. And we did this by migrating an IP database lookup. It's a very simple search algorithm that being offloaded into our device provides significant value to our customers. So how do we do that? There's a multi-stage process. This is a simplification of a very complex Apache traffic control architecture. You're welcome to go check that out as well. You and or I will want to look up and watch a movie. Say, for example, here in the United States, as I'm recording this, The Mandalorian comes out tonight. I'm very excited about that. So I'm going to be routed to this traffic router. He's going to go out and find the best local, closest high bandwidth version of that for me to watch. Send it back through the traffic router and go tell which server to actually deliver it to me for. Now there's an Ethernet connection and there's a large database sitting out and spinning media that doesn't have any acceleration to it whatsoever. And so what we did is we said, okay, these traffic routers can actually store information. So we're going to put a couple of our drives into the traffic router, remove the IPGeo database network-based lookup, but just use it locally because we have the CPUs on our devices to augment the traffic router and create this efficiency. So 2 devices plugged into a platform like this save 50% of that traffic routing lookup time. Fairly substantial improvement for these architectures. We're very excited to see how this moves forward. When you talk about greater than 10% overall efficiency, anything over 5% makes these guys really, really happy. So again, lightweight type of application, perfect for offloading into something as simple as a search and lookup. Great architectural development tool to use the OS on our drive to do work that was historically done by an OS in a big server platform. So next thing I want to talk to you about today is the concept of AWS. We're a qualified device for all of their Internet of Things usage models. There's this tool they have called Green Grass, and it's a group of architecture around a core devices and this use of Lambda functions in an edge analytic platform that talks to the cloud. But the problem with it still exists for that architecture is each of these individual devices are still talking to some endpoint. That endpoint is not powerful enough to truly do the work that is available to be done using this new architecture. So by what we've been able to do is deploy that Greengrass core and the Lambda function capabilities into every one of our devices as they're attached to the device that's actually using them to store the data and communicating directly with the cloud. So we're reducing latency throughout the entire system. It allows for flexibility of deployment and scalability of the platform without having to add a whole bunch of edge servers for the interaction of the end device storage product talking to a middleware storage device to then get to the cloud. And as you can tell by the fact that this is a certified platform solution, we've had some great success today with our friends at AWS. So the next architecture I'd like to talk about is the IoT Edge architecture from Microsoft Azure. We do have a 15-minute video on this that is on our website as well under the resources page. I'm going to show you just the demo portion of that. A little bit of the history of the technology and stuff that I've already shared with you is included in as part of that, so we don't need to get into that discussion. But what we've done here is we've been able to create the value of creating smaller platforms, lower power, lower cost, more economically viable solutions for our customers. In this particular implementation, we took away a workstation and we used a Raspberry Pi to connect a USB camera to the Raspberry Pi to ingest video, and then that video is then analyzed by the Azure IoT cloud. Now, we're actually not doing the work of the image analyzation on our device, but our device is acting as the direct connection through the host to the Azure cloud. So you're not sitting here waiting for the host CPU to do the work. We are utilizing cloud resources, but the fact that our device is directly connected to the cloud via a simple connection of NVMe is a groundbreaking architecture and a new way of looking and doing these types of architectures moving forward. So I'm going to switch gears here again. I'm going to go off video and I'm going to pull myself up and let me explain to you how our Azure IoT demo works. All right, so for our demo today, we're going to actually show how we're running the Azure IoT Edge on a computational storage device. So first thing we're going to do is we're going to create an IoT hub device, and you can see we're generating that here. Once that's created, we actually have to do some slight modifications in this instance for the Edge agent and hub. So what we're going to do is go in and actually change the runtime settings. And the reason we have to do this for our particular implementation is you can see there that current version is actually the Intel-based platform. And so we have to copy paste in the ARM beta version to be able to actually run the device in the ARM environment. So ARM is not fully released yet for Azure IoT Edge, so we're one of the beta testers for it. And now that we've got that updated, you can see we're able to go in and actually showcase that those particular devices are there. So now we need to do the final configuration at the device level. So we're going to go into our devices. You can see two screens here. The one on the right where we're typing now is the actual device itself. So root at node 1 is we're actually within the Linux subsystem of the storage device itself, putting that connection string in. The one on the left actually represents the host platform that the device is connected to. So we're now starting the IoT Edge platform. You can see that the Edge agent has popped up. We'll do a refresh again, and you'll see that we now have the agents and the host running. And all of this, again, is being done based on the storage device itself. So there's the hub and the agent. They're both running. We're using the Docker container application to do that. You can see there's the Linux instance being published. So now what we need to do is go in and refresh, and you can see the IoT server on Azure is now seeing these products as live solutions. We're next going to create a module here, and this particular one we're going to play with is an image analyzer. So we're going to utilize the capability of our system to actually run an image analysis application from the IoT hub on the individual device itself, in this case, the computer vision application. So we're putting in all the variables that are required to allow us to use this computer vision device. And you can see we're updating all of those services and creating a container option for us so that this service will now be able to be run as you would in any other particular IoT platform. So doing all the wonderful modifications that are required, you can see we've got this now Azure IoT Edge device set up and ready to go. There's our image analyzer module. So again, it's not currently reported by the host device. So now we've got to go in and again update, and you now see the image analyzer is running again within the Linux server on the device itself. And the next step for us to do here is then now actually take advantage of having the device speak specifically to the IoT Edge itself. So we're going to tell it to go ahead and run that particular tool. And you can see that it's looking for images. So basically what we've done is we've created a file on the Linux server within the device looking for pictures. So as a picture gets derived and allowed and stuck within the particular host device, you can see this is the Azure shell running on the website of the platform. Sorry, my mouse and I are having a little bit of a fun fight. But what we're doing is this Azure device is now live. So now we're going to run that on the actual Azure side. And now we've got both event monitors running. So for this particular one, I'm going to grab a picture of the Leaning Tower of Pisa. We want to see what that picture looks like. So we're going to grab the address for that image. We don't even need the physical image. We're going to now go to our host platform on the actual server device side, and we're going to store that image into the actual application device on the right. So on the left, we're physically copying an image from the web into the storage device that's shown on the right. And you can see where it says it just found that picture. It's gone out, grabbed the computer vision application, and has found and determined that we're now looking at the Leaning Tower of Pisa. So the storage device received an image stored by a host CPU sitting perfectly idle, and yet we were able to determine and use a computer vision algorithm from the IoT Edge on the actual storage device. So we're going to do it again. We're going to grab another picture. We're going to have some fun, and this time we're going to go from Italy to France, and we're going to grab a picture of the Eiffel Tower. So again, repeat the same process. We're going to take that image. We're going to actually physically store it on the storage device. So all the host platform is doing, similar to the example I mentioned, is storing the data onto the physical device.
Yeah, it's just a regular storage device, right? Regular SSD.
No, so it's storing it on the computational storage device, which is shown on the right-hand side. So we're looking at an output on the right of the storage device's Linux, but he's storing that picture on that storage device. So not only is it computing on it, but it's actually receiving inbound data from the host to process. Found the picture, and there we go. We are now seeing that it's gone out, and we have an Eiffel Tower. So as you can see, on that particular example, the host system was sitting there doing nothing but copying a physical version of a picture into one of our NG SSDs. And then this side of the device in that window was actually the device itself executing the code using the CPU resources that are built into every one of our drives. So again, another great example of how edge analytics and the ability to utilize onboard compute to make the entire application stack much easier to deal with, and the overall architecture less costly and more efficient. So another way we can look at it is when we get into technologies like machine learning and architectures around doing things with neural networks. So this is something that talks more to scale as we start to shift from edge-specific analytics now into more data center or even just edge POP type architectures. We looked at 4 different neural networks you can see there. 2 of them are highlighted as they're shown as the actual results on the screen between MobileNet and SqueezeNet. As we add devices, we start to see a growing, scalable, significant increase in value of each of these devices as we do this training speed for all of these architectures. The beauty of it is, as we start to do more training on the individual devices, you can see on the lower image there that the power consumed by each of these products is actually dropping from no drives doing the offload work versus all of the drives in that particular server doing the offload work. So one of the things that people like to ask when we get into this type of an architecture is we start to think about how to deploy these things. What is it that I'm going to do? What do I need in my system to make these things work? We start talking about what about GPUs? What about DPUs? What about other architectures like that? So this is showing us doing an object tracking application. And you can see we use the concepts of YOLO, GoTurn, KCF, MOS, and Wizard. A bunch of different tools that are available on the market today. And we did them running with the CPU. All the CPUs are in green. We even did a couple of them with some GPUs, and we did all of them with the offload into our devices. And what you'll see is the energy consumption on the vertical axis versus the accuracy across the bottom. So the higher the accuracy number, of course, the better the result. And the lower on the graph, the less power consumed. So with the exception of YOLO, where we do have one bit of a slightly improved capabilities to get an accurate image by roughly 0.2%, we actually have significantly lower power consumption in all of the architectures by using our device to do the work for the offload, while the GPU is still available to do resources. So it's not replacing GPUs, it's not replacing DPUs, it's taking advantage of all of these architectures together in a seamless fashion and putting the right product in the right place. So now what we've gotten through the edge, let's talk about some more fun architectures. So there's a whole bunch of different ways we can look at this as well. And some of these are about performance, some of these are about saving resources, and some of these are about doing things that make things cheaper. And so as we start to walk through all of these, the first one I want to get into with you today involves a partner company of ours. Dan Pollock from Data Storage Sciences, he's the CTO there, was working on a project around e-discovery. And his problem was, as you can see on the left in that cute little graphic, he had things coming in document form, picture form, PDF form, PowerPoint form, but he needed to search all of them in some form and fashion fast and efficiently. And the best way to do that with something like e-discovery is using an OCR tool, optical character recognition, but you need a text file to do that. So we worked with him, and he got access in this COVID environment to a remote access server in our lab and was able to deploy with very little effort a new architectural use of computational storage. So what I'm going to do is, again, go to another video clip for you. So we're going to shift gears and let Dan tell you exactly what he did to solve this problem for him, his architectural needs and his customers' needs.
Optical character recognition allows us to take images in, find any text in those images, and then provide that text output with a link to the image so that you'll be able to associate this image with that text, and you'll know that if there's something interesting in an image, you didn't have to read through every image manually to find all that interesting data. And then once that text is out of the image, but associated with the image, you can then index them together, and that creates a searchable archive, and that enables e-discovery, and that's sort of useful for things like legal work and document management and all kinds of useful applications. So like I said, I'm taking the computational storage devices from NGD Systems, building a storage system out of them using open source software. In this case, it's MinIO, and I'm building an object storage cluster. I'm putting files into the MinIO storage cluster with the S3 API, which is basically an AWS developed object standard. And when that file gets into the storage system, if it's of a specific type, I'm launching a webhook that runs some software that performs optical character recognition on images and then stores a text version of the file that only has the text from the images in it. And we'll show you that demo. But here's how it works sort of at a high level, just so you can see the picture as opposed to me telling you how it works, right? So files go in, the object store accepts them, the computational backend performs optical character recognition on them, stores a text version of the file that only contains the text that was in the image, and rinse and repeat. And the nifty thing here is that the simple act of storing the file creates the output of the text object. You don't have to do anything. You don't have to invoke any additional processes. It's all just running in the background as part of the storage system continuously. So there isn't a separate process, and there isn't any additional capability or hardware that you need to make this happen. Just having the code written and running on the computational storage system creates that capability, which is secondary to the primary role of the storage system, which is obviously storage, but it gives you this sort of nifty additional function that if you are interested in, you get for basically free. And so here's the demo buffer here. Let's do, so I'm going to copy those files into the buffer or into the storage system. That looks right. So that's one of the files in. Let's put a second one in. Oops. Okay, so those two files are in, and the system will have processed them. Just to give you an idea of what they are. Here's the barcode. So obviously you can see there's barcode and the QR code and some numbers. So that's what we would expect the system to recognize. And I'll put that there. And now we'll do, I'll take a look at the text version of that. And there's the text output of that file. I believe that's correct. So clearly I've taken an image, from this document, which is basically just barcode, which is decent enough, simple, straightforward. And I've created the text representation of that, which now I can then index. And so if I'm looking for this barcode for some reason, I know that I have this somewhere and I know what's in it. I don't have to wonder what that barcode is. And that's kind of a nifty thing. I'm gonna look at the QR code. So that's the text representation of the QR code. And I'll show you the QR code actual as well. So this is a bill and it has this QR code, which is why it's called that. But you can see that the text from the bill is effectively more or less optically recognized and transformed into text in this file. And obviously,
so I'm back and I wanted to be able to talk to you about what was happening there. So as you can tell, again, Dan works for an organization which is helping folks like the US Patent Office or other folks that would need to take in a massive amount of documentation in multiple forms and frames and convert it into a searchable and text format. Now, this is something that we've been working with him for some time on. We're getting ready to deploy it with some customers as well, and has a lot of flexibility in the marketplace to be able to deploy. Again, the highest level part of this, and hopefully it was conveyed from Dan effectively, is that he did very little in the way of any code manipulation. All he did was migrate a tool he already uses from a host CPU into our storage device to make that thing work much more efficiently. So again, e-discovery, AI, search, all of these tools are great, easy things for us to deploy in our flexible and keep it seamless and simple KISS principal product. So I've stepped outside, thought I'd give you a shot of what the NGD offices look like. This is a great view from our space back in about July timeframe. So still a little sunny. I mean, it is Southern California, but I thought it would be good to at least highlight where we're at and give you another view aside from the bridge of the USS Discovery. So next up, compression. Again, this is something that looks from a very scalable perspective. The more devices you have, the more offload you get, the more compression capabilities or decompression capabilities that we can provide. Now, one thing to note here that's very interesting is the two competing devices that are here are standard off-the-shelf SSDs. Those SSDs are enterprise cache ultra write performance drives. So even though those devices actually have a faster throughput than my product, my ability to scale the offload of that feature and be able to allow the host to do other work and not block the use of the solution by the CPU itself highlights that computational storage is a solution to this one-to-many problem that the CPU and storage has previously existed. And you can even see that from the example on the energy consumption again to the right. It's all about power and performance, but not your IOPS, not your megabytes per second, but how the application, the solution, and the architecture can take advantage of something as unique and innovative as this while making it simple and seamless. And so how do we do that? Here's an example we did with Microsoft Research. This is a concept of a nearest neighbor search. So Facebook has an algorithm called Facebook Artificial Intelligence Similarity Search, FACE. It takes an image, converts it into a vector, 3D weighted vector. So it's basically a search engine. That search engine, as you can see in the host-only architectures here, takes longer to move the text features from a storage device into host memory, then search it, flush it, and repeat. It takes longer to load the images than to do the work. It's a perfect example of why not moving data is important and computational storage has value. Now, 8 drives brings that down by almost 85%. A full server, 95% of that moving of data is removed, and the search time is dropped by more than 60%. So I went from taking what would be close to 75 seconds to do a search of 1 million images down to just under 12. That's invaluable, but it's so hard to convey without the ability to work with partners like Microsoft to show that value. And of course, less time, less CPU, considerably less power as well, so 60% or greater power. Today, we're sitting about 1 billion images in these databases. By this time next year, it's going to be trillion images. So as these continue to grow, being able to rescale these architectures like you see here is very, very valuable to all of our customers. And the ability to say, computational storage has the ease of use and the flexibility and the scalable capabilities to support today's architectures and beyond. Now, It's not always about performance. It is about host resources. So we have another customer who uses Elasticsearch. Elasticsearch is historically memory heavy, uses a lot of DRAM. Everything has to be resident in memory, very similar to what was happening with the previous example. But this customer wasn't looking for performance. They wanted their DRAM back. And so we said, okay, let's take the system shown on the top right. Let's offload some of the work to our drives. So we reduced the DRAM consumption by half. We reduced the CPU consumption by a little more than half. And then we said, well, what if we run it completely on our drive only? Check it out, folks. 0.01 gigabytes of DRAM required to do any of that work. 0.79% of the CPU is needed. That is telling me, and it should be telling you, the host can go do whatever it needs to do, and this search that's required gets done fast, efficient, and with very, very little additional resources. And we're not rewriting tools. We're simply executing a built-in application of Elasticsearch inside the storage device and letting the host go do other work. So significant value to a lot of different aspects and workplaces for different customers in this particular architecture. Now, we also have the concept of MongoDB. This one, the customer said, I want it cheaper, not cheap, right? Nothing's ever cheap in this world. They wanted to be able to do something with a little less effort and a little more performance and capability. So in this case, we reduced CapEx by 40% and OpEx by 30%. And this is based on a 3-year lifetime. And this is keeping the fact that we're using computational storage engines, much like in the VMware example, to do the sharding and replication services that are usually done at a CPU level. So fewer CPUs, we have higher density SSDs than we do HDDs in the off-the-shelf example. So our SSD solution with compute enabled, so computational storage drives, all based on flash, is actually cheaper than a hard drive based architecture. So yes, folks, death to the spinning media. It is capable to be done. There will always be a need to archive, do other things with spinning media. But moving forward, flash is key, and using the flash in a way that's never been thought of before with the concepts of compute enabled devices and a seamless, simple programming model allow us to give a customer these kinds of savings in a deployment. And performance is light. So that was the goal, was get light performance, light capacity, and lower the total cost of ownership. So flash media, cheaper than spinning media hard drives, reduce server count, reduce cost, reduce everything, and still have value to the platform. So how do we do this? I've given you lots of examples. I wanted to spend time at the first half of this showing it in action. We do it by enabling products in your standard everyday traditional architectures. M.2 devices, U.2 devices, and now the new E1 short that we launched last week, or about 2 weeks ago, depending on when this video airs. A 12 terabyte drive in an E1 short that has compute capability. You can see the capacities are going to continue to increase as we move to QLC-based solutions. All of these devices have the same core architecture, same capability, focused on high density, low power, compute capable solutions. Now, we do it by enabling a unique architecture where we've embedded ARM cores into each of the devices. That's where those CPUs that we've been talking about come from. And so that's done via everything over NVMe. You plug it in, it's an NVMe drive, it's an SSD, it can do compute. We have a host agent, we call it an API here, relatively like an API. It's not exactly an API, but it's currently a NGD standardized product moving forward, working with the SNIA computational storage twig and the NVMe computational storage task force to make sure that these architectures are aligned with this industry standard. So our solution is built on a ASIC solution that we've designed. It's PCIe Gen 3 with Gen 4 coming. All of the things you need to make our flash device work, all of the firmware, modular capabilities, and also support of all the different devices. So I'm not a Samsung, I'm not an Intel, I'm not a Micron. I use them all. So if you have a preferred vendor, that's not a problem. If you have a capacity target you're looking for, we can pick the vendor that has this die stack that makes the optimized hardware more efficient. And then you have all of the in-situ processing stack alongside that with the OS, the virtualization capability, even hardware acceleration, and encryption capabilities. So there's a lot of flexibility in these particular platforms. So at the end of the day, what does this really mean to you, me, and everyone else in the market? People notice that our technology is of value and is better than a lot of the other products in the space. So this is a recent IT Brand Pulse survey that was announced at the Flash Memory Summit in the US a few weeks ago. and we became listed as the market leader. And not only did we take that leadership position, there's a little bit of a clear notification of how well our product and our solution can enable, will enable, and does enable customers to keep us in the forefront of the computational storage solutions today. We do it because we're simple, scalable, and low cost. FPGAs are what are the building blocks for everyone else's devices. We got rid of our FPGA solution in 2019. We originally had FPGA solutions in 16 and 17, so we're that far ahead of the marketplace today in our ability to derive and drive value added from these solutions. Another aspect of what shows computational storage has value in the marketplace today, Gartner is a great resource for all kinds of information. This is important for you to realize that not only did we enter a hype cycle, and yes, we're on the early edge, I get it, folks, we're not in the perfect plateau of productivity, and we'll get there, don't get me wrong, but we're in two. Very few architectures are able to cross over from a technology like ours to be both a storage solution and a compute solution and drive value for customers. And you can see here I've highlighted below, CS increases the performance per watt ratio, decreasing power for applications at the edge, and has material performance benefits. This is coming from leading researchers at Gartner. Again, the whole marketplace is going to continue to grow, be driven by these architectures, and we're very excited to continue to ride this wave. We're going to take it up, over, and beyond into a wonderful moving forward architecture. So our platform is very strongly supported with an IP portfolio of about 40 patents, and we've been working with the National Science Foundation as well as other organizations within the US for closure of grant work, which means the US government at this point sees value in these technologies, and we are excited to continue that work moving forward. And we've got an entire innovation portfolio that's built around the pillars of success for both storage devices and compute-enabled solutions. So with that, I'm going to let it be there. I know we can't really do live Q&A. I should be online for this event. It's going to be a little late my time, early your time. But hey, we're going to have some fun. And if you have questions, I'm available offline as well. Looking forward to the feedback on the event. Please don't forget to provide some of that ratings. It helps the SNIA organization. So as I put my SNIA hat back on, we appreciate you participating in our event this year. It's very important that we continue to work together through this incredibly unique environment and drive forward innovation and technology across the world as we're staying in our local regions. So thank you again for your time today. I'm going to go ahead and bid you adieu. Hope you had a great time listening and learning something new about computational storage. Tried to keep it entertaining and light. And so with that, may the flash be with you, and to boldly go where no storage has gone before. I'm going to use them all, folks, because it's fun to talk about innovative technologies in ways we've never thought of them before. So hope you enjoy the rest of the event. Hope you've enjoyed the event that you've had so far today. And if you have any follow-up, please do let me know. Thanks again. This is Scott Shadley with NGD Systems. Have a great day.